Welcome to The Explainer. Today, we're going to peel back the layers of the robot operating system 2, not just to see what it does, but really how its whole architecture was completely rethought for the future of robotics. And really, that's the perfect question to kick things off. I mean, ROS1 was a huge success, right? Thousands of developers loved it. So to really get ROS2, we first have to ask, why? What problems was it actually built to solve that ROS1 couldn't?
And the answer really boils down to a massive shift in thinking, a move away from a tool that was perfect for the academic lab and toward a framework that had to be ready for the real world, for commercial products, for mission-critical stuff.
All right, so let's break this down. The biggest, most fundamental change is right there in the architecture. You see, ROS1, it had this central master node. It was the traffic cop for the whole system. And if that master went down, poof, the whole system collapsed. So ROS2's first big move was to get rid of that single point of failure completely. It went decentralized, adopting an industry-standard communication system called DDS. And that right there brings us to the absolute bedrock of ROS2, the Data Distribution Service, or DDS. And I gotta say, if you want to understand ROS2, you have to understand DDS. It's not just some feature they bolted on, it's the entire foundation.
So the core concept behind DDS is this thing called the global data space. Now, the best way to wrap your head around this is to just forget everything you know about sending messages from point A to point B. Instead, picture a shared digital whiteboard. One of your robot's nodes, say the one tracking its position, just writes that position onto the board. And any other node that needs that info, it just looks at the board and sees the update instantly. It's the difference between sending a letter and everyone looking at the same live collaborative document.
Okay, so if DDS is doing all this heavy lifting under the hood, how does ROS2 still feel, well, like ROS? As you can see here, it's pretty clever. A ROS2 publisher or subscription isn't some brand new invention. It's really just a clean, user-friendly wrapper around these more powerful underlying DDS parts. You could almost think of it like ROS2 providing a simple, easy-to-read menu, while DDS is the super complex professional kitchen in the back, doing all the hard work. Right, so if there's no central master, how in the world do all these nodes find each other? Well, it happens automatically in this kind of two-step discovery dance. First, a new node joins the network and basically shouts out to everyone, "Hey, I'm here," using a multicast message. Then, once other nodes hear it, they start a more private, one-on-one conversation to swap the important details, like, okay, what are you publishing and what are you subscribing to? It's all automatic. All right, let's move one layer up the stack. We've established the DDS is an industry standard, but here's the thing. There isn't just one DDS. There are multiple companies that make DDS software. You've got eProsima, RTI, Eclipse, a bunch of them. So how does ROS2 deal with that? How does it avoid getting locked into just one? It does it with this absolutely brilliant piece of abstraction called the RMW layer, which stands for ROS Middleware Interface. And honestly, the best way to think about it is as a universal travel adapter for your code. You've got your C++ or Python code, that's your plug, and the RMW layer lets you connect it to any DDS wall socket you want, without ever having to change your plug. And the thinking behind this RMW layer is all about future-proofing and giving you, the developer, total flexibility. By keeping the interface minimal, only the essentials, and using a universal C language API, it means you're never, ever locked into a single DDS vendor. You can pick the one that's best for your project. And hey, if some new, amazing middleware comes along in the future that isn't even DDS, the door is still open. Okay, so our communication layer is sorted out. Now we need to actually build the familiar ROS logic on top of it. You know, the concepts we use every day, like nodes, parameters, timers. And that's the job of the next layer up, the ROCL client library, or RCL. And this is really the don't repeat yourself principle in action. See, instead of having to re-implement the core logic for how a node works in C++, and then do it all over again in Python, and then again in Rust, or whatever comes next, it's all defined once in this central C library. And this is huge because it guarantees that a node behaves exactly like a node no matter what language you're writing your code in.
Then, sitting on top of that central logic, you get the language-specific client libraries that we actually write our code with. The best way to think about RCCP for C++ and RCPy for Python is like different desktop environments, like Windows versus Mac OS. They look and feel different, and they're definitely optimized for different jobs. C++ for that raw, high-speed performance, and Python for rapid development and scripting. But underneath it all, they're both built on the exact same powerful kernel, that core RCL.
Okay, so we've built up all these layers, from the DDS foundation to the client libraries. So how do the common communication patterns that we use every single day, I'm talking about things like services and actions, how are they actually put together?
Well, this really shows a core philosophy of ROS2: build complex tools out of simple, fundamental parts. A service, right? It feels like a single request and reply transaction. But here's the secret. It's not actually a fundamental building block. It's really just a clever pattern that uses two hidden topics under the hood, one for sending the request and another for getting the reply back.
So if that's what a simple service is made of, what about a more complex action? The pattern we use for those long-running tasks, like telling a robot to navigate to a goal. It needs to give us feedback along the way. We need to be able to cancel it. How many topics and services do you think something like that takes?
The answer? 5. That's right, a single ROS2 action is actually a pretty sophisticated pattern made up of 5 separate communication endpoints all working together. Yeah, it's pretty wild. An action is actually made of 3 different services and 2 topics, all choreographed to manage the goal's entire lifecycle. But here's the beautiful part. All of that complexity is completely hidden from you as the developer. You just interact with a simple action client object in your code, and the client library handles all 5 of those endpoints for you behind the scenes. All right, we've gone pretty deep into the stack, so let's pull back up for a second and talk about what all this architectural detail actually means for you, the developer, in your day-to-day work. What it all boils down to is that ROS2's design is a series of very deliberate trade-offs. On one hand, you get this incredible flexibility. You can choose your middleware, you can fine-tune communication for extreme reliability using something called QoS, or quality of service, and the decentralized design is super robust. But all that power comes with a cost. There's definitely a steeper learning curve than ROS1. Understanding things like network discovery and QoS settings, it isn't really optional anymore. It's a core part of the experience.
And that really leaves us with a final thought to chew on. This architecture was built to balance power against complexity for today's industrial and multi-robot challenges. So by understanding these foundations, this constant tug of war between power and usability, we're in a much better position to imagine and maybe even help build whatever comes next for robotics. Thanks for joining me for this explainer.